Welcome back everyone to the great video where we're gonna review all the basic differentiation skills we need students to know when they pass Calculus 1 class in order to move on into further studies. And there's not so many actually, there's only 6 topics, but they are the basics of the future work we're going to do. And soon we're gonna require you to be very fluent with all of these, very fast, very professional. And you will be surprised in the future to see that all the science you know cannot live without those rules, and all scientists in any areas actually do perform these differentiation techniques. So what did we learn? No matter what school you're in class you're in, we need you to know after Calculus 1 class some basic derivative formulas like power rule, derivative of sine and cosine, then product rule and quotient rule, chain rule, that's your favorite one, I know, implicit differentiation, that's the one that takes a while, derivative of exponential logarithmic functions, that's the fun ones, and inverse trigonometric functions, those are the creepy ones that have fractions and square roots usually. So grab your pencil, grab a paper, and let's do it. The goal of this video is to briefly go over these topics, and then if you feel uncomfortable with any topic, you put a huge fat star or any kind of note on that example, and then go and watch my other videos on that particular topic. 2 examples and you'll be professional again, and move on. Maybe it's also helpful to pause the video when I start the example, do it by yourself, then run the video and see if my solution matches with your solution and if my steps match with your steps. Sometimes the order might be different, which is fine. After all, differentiation is a pretty creative process. So let's review some basic stuff like power rule, n goes down, x times n to minus 1. Some handy note over here is to remember what to do if you deal with radicals or square roots or anything like that. If you have a square root and you feel not comfortable with it, you can always transform it into the exponent with a fraction. Now, some kind of interesting little things. What is derivative of square root of x? You can either use this rule I just showed and then rewrite it as x to 1/2. Then when you differentiate that, 1/2 goes down and x will be raised to the negative 1/2. Or you can remember it's 1/2 square root of x, the same thing. What is 1/x prime? You can also rewrite it as x to the negative 1. Negative 1 goes down, x becomes x to the negative 2, which is negative 1/x squared. It's up to you to decide if you want to be faster and remember these formulas, or just rewrite first and then differentiate without making mistakes. Okay, product rule and quotient rule is taught differently in different schools. The law is the same, but notation is different. This is the way I teach it because it's very fast to write. U times V prime is U prime V plus UV prime. You see, it's even fast to say. That's a product rule. U over V prime is always start with the denominator and just square it. I recommend to do that first because students tend to forget to do it later. Then in the numerator, you basically have a product rule but with negative sign. Since there is a negative sign, the order matters. First, you differentiate the numerator times not change denominator minus copy the numerator, differentiate the denominator. Maybe the order can be changed, this order can be changed, and this order can be changed because it's a product. But do not change the order. Which one goes first? The couple with u prime goes first. If you changed accidentally the order, your answer will be correct but with a negative sign. Then trigonometric functions. We definitely need you to know that derivative of sine is cosine, derivative of cosine is negative sine. Basically, cosine is the guy that always behaves weirdly. Remember, sine at 0 is 0, cosine at 0 is not 0, it's 1, and so on. So that's how I remembered. Cosine is weird. So cosine gives you troubles, and that's why when you differentiate it, it gives you negative sign. Then tangent gives you secant squared. secant likes itself so much that it copies itself first, and then you multiply by tangent. And then the other two, cosecant does the same thing. It likes itself and then times cotangent instead of tangent. And just like cosine, cosecant gives you troubles, so there's a negative sign in front of it. And cotangent gives you negative sign, and that's cosecant squared versus secant squared for tangent. We definitely require you to know all of this, but I would tell you that the first three are extremely important, and they're very common, these three. And derivative of secant happens pretty often. So these four definitely you should know. The other two, we need you to know that as well, but you will see it not as often as these four. Now, exponential functions and logs, derivative of e to the x is e to the x, copy itself. Derivative of log is 1 over x. If you imagine that you're talking about e to the u, where u is some kind of function, then based on the chain rule, you copy it and then times derivative of the function at the exponent. So that's the case of the chain rule. As you can see, I did not provide you any formula for the chain rule because the formula is basically differentiate the function outside times the derivative of the function inside. Chain rule is better to practice more and more, then you get familiar with it better than to just remember the formula. We also needed to know that if the base is not e, then a to the x prime still copy, but then times natural log of a. We actually do times natural log of e for the case with e to the x, but natural log of e is 1. Same with log base a. You still have 1 over x, just like before, but then also divide by the natural log of the base. We do actually divide by the natural log of e in this case, but again, it is 1. Laws of logs will be important. Log of the quotient is difference of logs. Log of the product is sum of logs if they have the same basis. And the most pretty cool one is log of the a to the x is x times log. So x goes down, well, basically you multiply by x. These properties allow you to slow down the process because division, product, and exponential functions are pretty time consuming, especially if you talk about coding in the computer. Log instead creates differences, sums, and products from these processes, so it slows down the situation. Laws of logs. And the last topic, derivative of inverse functions. And usually I like teaching it using u notation, where u can be any kind of function in case of the chain rule. Arcsine, or sine minus 1 of u, is 1 over square root 1 minus u squared. And if this u is a function, then you later multiply by u prime. Make sense? And usually I put it in the numerator right away. Arc cosine, or cosine minus 1 of u, will be minus 1 over. Remember that cosine gives you negative 1 all the time, so arc cosine does the same thing. Minus 1 over, and the same thing, square root of 1 minus u squared. Arctangent doesn't have a square root, and it has plus sign at the bottom, so it's 1 over 1 plus u squared. I usually say it out loud this way. Arctangent of the input is 1 over 1 plus input squared, no matter what this input is, even if it's a crazy function, and then times derivative of that input, if there is a chain rule involved. And then check out the cotangent, arccotangent, arcsecant, arccosecant. The most popular ones are the first three. So definitely know these three, and then the last three will show up as well, but hopefully will not, because I think it's really enough to know. Okay, let's practice. And you will see that I'm not going in order because there's so many things to practice. And basically I will mix up examples. I will mix up chain rule, and then product rule, quotient rules, and then I will do implicit differentiation, logarithmic differentiation, and inverse trigonometric functions. For example, find a derivative of say we have cosine cube of x times x squared minus 2. Okay, that's product rule. I can see u times v. The first function will involve chain rule because cosine is cubed. Let's do it. Y prime or dy over dx, that's the same thing, just for you to know, is derivative of u requires chain rule. 3 goes down, cosine x, change the exponent to 2, decrease by 1, times derivative of the function inside, which is negative sine x, and that was only derivative of u, that was u prime. Copy v, x squared minus 2, now plus copy u, cosine cube x times derivative of v is 2x. The order can be different, depends how do you like to put it. So you can do you can switch order between these guys, and between the couples as well. Since it's a product in addition, it doesn't make big difference. So you decide. Depends how you got used to do it. That's it, that's a good answer, unless we require you to simplify. If you will see this on a test and you have a multiple choice answers, then you're supposed to match it with a multiple choice, and probably you will have to simplify it somehow. Second one, how about I'm gonna do chain rule several times. For example, sine to the 5th power of x to the 7 minus 2x. How do I know that this is chain rule several times? Because sine is raised to the 5th power. And if you don't understand which one goes first, think about it as sine of x to the 7 minus 2x, and everything is raised to the 5th power. So it is actually a polynomial first, something raised to the 5th power. Then when I want to differentiate that, 5 goes down, copy everything inside, sine to the x to the 7 minus 2x, change the exponent to 4 times, now I can differentiate the function inside. What do you see inside? I see sine of something, some kind of angle, and that angle is x to the 7 minus 2x. Derivative of sine is cosine, copy that angle, do not change it, copy. Too early, you cannot reach it yet. And then finally times the derivative of the function inside. What is the inside function? X to the 7 minus 2x, which is 7x to the 6 minus 2. That's chain rule twice. Chain rule twice. Basically, to illustrate the situation, I can explain it to you using Russian dolls. Do you know what Russian doll is? Well, that's a toy. It looks like this. It's my ugly Russian doll. And then it has many smaller Russian dolls inside. So the function outside was some f raised to the 5th power. Then, when we differentiated f to the 5th power, it gave us 5f to the 4. 5f to the 4. Then, only now you could unlock the next level of the Russian doll. So you open the outside layer, and now you see that f is actually sine of some kind of u, but you don't see what u is. Well, derivative of sine u was cosine of that u. That's why I'm copying the angle and don't touching it. When I finish doing that, finally I can unlock the last layer, the third one, and then I can see that u is actually a polynomial, which is 7x to the 6 minus 2. Derivative of that is, oh no, that's not the one. That's right, that is already derivative. The function inside was x to the 7, x to the 7 minus 2x, and that's the inner part. So after all, we had f to the 5 of u of, f of to the 5 of u. Or you can even say that the outside function was, say, g of f of u. So that's how the Russian doll would look like. Sometimes we teach it using onion. We like peeling onion layer by layer. And that's what the idea of the chain rule is. Chain rule basically undoing product rule. And that's why you can see you have products over here. And how to undo it? You use chain rule to undo whatever is inside. More examples. So again, if you don't feel comfortable with this right now, then put a star, say like that, a fat star. And that fat star in the future will tell you that this is where you struggle with. Then go to my videos. I have a whole list of videos called Mastering Differentiation, because that's what we wanted to do. We wanted to be really good at differentiation, to master it, no matter in what degree you're gonna go after that. Engineering or microbiology or math major or computer science, you have to be good at this. That might be part of your job in the future. Third example, a question for you. If I'm working with y, which is 2,000 all over, say, sine of 5x cubed. Is this a quotient rule or not? You can do a quotient rule if you want. It's going to be u over v, but that's a longer path to do. What is the shorter path? Who knows? Yes, let's rewrite the denominator, which is sine of 5x cubed, with a negative exponent, and then differentiate that using chain rule instead of the quotient rule. It will be negative 2,000 because negative 1 goes down. Sine of 5x cubed raised to negative 2, decreased by 1, times, differentiate the function inside, which is sine. Now it becomes cosine 5x cubed, times, finally differentiating the function inside, which is 15x squared. Did you catch up? Chain rule twice. Or you can use quotient rule, and I will do it just in this case to compare for you which one is faster. Quotient rule tells me, or quotient rule. So I will do like this. Use chain rule, and that one is preferable method. It's faster. Or use quotient rule. And then for the quotient rule, I'm recommending to square the denominator first. Now, derivative of the top is derivative of 2,000. What is derivative of 2,000? Yes, that's 0 because it's a constant. Then doesn't even matter what comes after this when you multiply, because everything times 0 is 0. But if you want to follow the rule, you can write down sine 5x cubed over here, but the whole first term will be 0. Minus, copy the numerator 2,000 times derivative of sine of 5x cubed is cosine of 5x cubed times 15x squared. Chain rule, but this time once. So this is derivative of the denominator. Now when you simplify, the answer will be the same. Let's see. Negative 2,000 of times cosine of 5x cubed times, well, 15x squared, you can actually multiply by 2,000, all over sine 5x cubed squared. And this is the final answer. And now decide which way was faster to do, this way or the chain rule. I do think that chain rule was faster, so I usually prefer doing chain rule. But if you're afraid of working with chain rule, then you don't have to. So, I also want to point out that you do also need to remember what is it 1 over sine. Do you remember what is 1 over sine? There's such a thing as secant and cosecant, so definitely remember these guys and use them when needed. For example, you can also rewrite this piece over here as cosecant squared, right? Because 1 over sine is cosecant. So definitely review these guys. I want to also point out that at the beginning over here, I have it in my notes, so let's not forget. Sine to the negative 1 of, let's do u. That's arc sine of u. That's inverse function. But sine of u to the negative 1, that's 1 over sine u. So the negative 1 right on top of the sine or cosine or tangent or cotangent and so on is reserved for the inverse trigonometric functions. That's why if I want to point out that this is 1 over sine, I'm using the huge parentheses like this. Okay, not too bad. Now, how about more examples? Like moving on into something more challenging, which for example involve more trigonometric functions. Then of course logarithmic functions should be checked out. Don't forget about that. We're gonna do logarithmic differentiation and implicit differentiation as well. Okay, let's practice inverse trigonometric functions. What is gonna happen if I ask you to differentiate arctangent or tangent minus 1 of 2 over x cubed? Okay, I don't have a good memory, but I remember that arc sine and arc cosine have a fraction, plus or minus, and a square root, right? And then 1 minus u squared. But arctangent has no square root and there is an addition at the denominator. So this is how I will say it out loud. Arctangent of u, and this is my u in red, this is my u, is 1 plus u squared, 2 over x cubed, and everything squared. Then I will do times the derivative of the function inside. Then if you're not very confident with 2 over x cubed, rewrite it as 2 times x to the negative 3, right? And differentiate that. What is the derivative of 2 times x to the negative 3? Is going to be negative 6x to the negative 4. And usually what I like to do, instead of doing times, I just did it for you to know what's going on. I like putting it right away into numerator. Then it just saves a lot of space, as you can see. Then you don't even have to put parentheses. So that fraction actually is the final good answer. If you want to simplify a little bit, you can say that this is negative 6 and the top, x to the 4 can go to the bottom because of the negative exponent, times 1 plus 2 squared is 4, x cubed squared is x to the 5 or x to the 6. Remember that x raised to the a and then b is actually x, a times b, right? So I need to multiply 3 times 2. That's going to be 6. You can simplify even more to get a better answer. If you have multiple choice part on the exam, maybe you want to distribute x to the 4 and so on. But I like it this way. Now, how about mixing exponential functions and inverse trigonometric functions? What is the derivative of arc sine of e to the 7x? Let's do it step by step. Arc sine, I remember, is positive because sine doesn't give me troubles. I remember it's 1 over a square root and then 1 minus input squared. Input squared. So it's going to be e to the 7x. That's my input. squared, don't forget that, times, and I will put it in the numerator with a green color, derivative of the function inside. The function inside is exponential function. Exponential function copies itself when you differentiate it. But then don't forget to multiply by the derivative of the exponent. That's 7. So the final answer looks like 7e to the 7x all over a square root 1 minus e to the 14x, because 7x times 2 is 14. That's a good answer. More examples. What if you're working with logarithmic functions with different bases and exponential function with different bases? What is derivative of sine of natural log of x squared minus 7 to 10x cubed? Just made this up like on the way. Okay, let's see. So sine gives me cosine. I know that. Copy the angle. Don't change that. ln x squared. Just like with the Russian doll, you cannot enter that piece until you finish differentiating the piece outside. So basically we're taking the derivative at the previous step. So cosine at natural log of x squared. Now I look one step inside. And what do I see? I see log of something. Log of something gives me 1 over that something. So that's going to be 1 over x squared. Times, now I'm looking inside of the function, and that's x squared. So that's going to be 2x. Did you catch up? Did you pause the video to try it yourself first? That would be very handy. Minus. The next part, okay, I see exponential function, 7 to the 10x cubed. Exponential function copies itself, 7 to the 10x cubed. Then I notice that the base is not e, so I will do times the natural log of 7. And that's just the exponential part. Times, chain rule steps in, that's my chain rule. The chain rule says don't forget to look over here at the exponent part and differentiate that. It becomes 30x squared. Basically, if you never differentiated all the pieces you see, probably you missed a step. That's what I would say. If there is 10x cubed somewhere, you have to at some point differentiate 10x cubed. If there is ln of x squared, you have to differentiate both ln and x squared at some point. We can simplify that a little bit. Then it will become cosine of natural log of x squared times 2x over x squared will become 2 over x minus 7 times 3, 21, 0. Oh, you cannot simplify that actually, because it's 7 raised to the 10x cubed times natural log of 7, that's a constant, times 30x squared. Okay, nothing to simplify here. And this is the final answer. Finally, let's move on into longer problems. Basically, the longest two problems are implicit differentiation and logarithmic differentiation. Let's do the implicit differentiation problem 7. Implicit differentiation. Implicit differentiation is a very powerful tool. Differentiation is a very powerful tool that allows you to differentiate everything you see right away. If I don't give you y equals blah blah blah, then how can you find y prime equals blah blah blah? Question mark. Because whatever I did before, I always gave you y explicitly. Well, if y is not given explicitly, but instead of it is given implicitly, then you differentiate implicitly. For example, x times y cubed plus 10 y to the 11 equals 9. Let's do 900. Why not? Then I cannot solve for y to find y prime, right? If I cannot find y implicitly, and sometimes I just really don't want to, then I can find y prime explicitly, avoiding the step of finding y by itself. But when I'm gonna do implicit differentiation, you should keep in mind that one function here is cool and the other one is not cool. And what I mean here is that the y function depends on x. That's why it's called dependent variable. Dependent variable. That means every time I have some kind of derivative that involves y, the derivative of y will be y prime. That's basically based on the chain rule. But x is just x, and it's called independent variable. That's not a cool one. Independent variable. Every time I differentiate y, what is derivative, not y, x, what is derivative of x? It's just 1. So one derivative is not the same as the other one. So keep those two things in mind. Which one is the cool one and which one is not? The cool one basically is y that has x inside in the Russian doll. That's the idea. Let's start differentiation. X times y cubed, that's the product rule. X is u, v is y cubed. Product rule tells me differentiate x, derivative of x is 1, copy your y cube, copied, plus copy x, differentiate y cube, that's chain rule. First I see function cube, that's 3y squared. But then every time I have to deal with y when I'm differentiating, dy prime pops out. If you like the notation of dy or dx, that's good as well, and actually that counts to be more professional. So you can write down dy over dx everywhere. I teach with the y prime notation in Calculus 1 class because it's faster. However, at some point when we're gonna add more variables in Calculus 2 and 3, you will have y of x, and then maybe t as time, maybe m as mass of some object. Then when I ask you to find y prime, the question will be which one? With respect to x, with respect to t, with respect to m. That's why the notation dy with respect to, say, t will be more clear. It will say this is the derivative of the function with respect to time, or the speed of the function with respect to time versus mass or position x. That's just a side note. So you can be more professional from the beginning, but for the testing purposes, y prime is faster. So what did we do? That was just a derivative of the first term, x times y cubed, and the first y prime already popped out. Now 10y to the 11 becomes 111 y to the 10 times y prime, remember, pops out again, equals 900. True or not? Many students get excited that they finished differentiating the left-hand side, which was challenging, and then they forget that you actually have to differentiate the right-hand side. So don't forget, you have to differentiate 900 as well. Derivative of 900 is 0. Good job if you caught the mistake. Step 2, that was step 1 on implicit differentiation. Step 2, locate pieces that involve y prime and move them to one side. I usually move them to the left-hand side. X, I will do 3x y squared times y prime plus 110 y to the 10 times y prime equals. I was lucky those pieces were already on the left-hand side. Then whatever is not involving y prime should be moved to the right-hand side. I will change the sign. It will be negative y cubed. Now I'm locating y primes again and factoring them out. That's step 3. Some people combine step 3 and step 2 in one if you're already fluent with implicit differentiation, and that will save you time. 3x y squared plus 110 y to the 10 equals negative y cubed. The fourth steps is always the same. It gives you the answer. Y prime equals And it's always going to be right-hand side RHS all over those brackets you have when you factor it out in the previous step. So it's going to be y prime equals minus y cubed all over 3x y squared plus 110 y to the 10. And that's the answer. Was it fast for you? Did you catch up when you did it yourself? Are you fluent with all those products and quotients and so on when you do implicit differentiation? Put a fat star if you're not and watch other videos with implicit differentiation. I promise you, if you do it several times, you become very good at it. Now, the last thing to review, left, do you know what? We did actually everything except, exactly, logarithmic differentiation. So that's going to be number 8. Number 8, logarithmic differentiation. For doing logarithmic differentiation, you need to know laws of logs. When do we recommend to use logarithmic differentiation? So use when you have cases like complicate fractions. So y is some kind of fraction with product rule and quotient rule mixed up. And we're going to do that example right now with some kind of fraction. I don't see it in my notes, but I guess I can just make up some. Yes. Okay, fine. Then I'll just create a random fraction. For example, you're working with x5 minus 7 squared, and then there's going to be something like 3x squared times, and you will have, I will even do times, and then we'll do 7x 5 and minus 3 to the 5. Nice. Something like this. In this case, logarithmic differentiation will be a win-win, because do you really want to handle right now the quotient rule u over v case, and then the numerator will force you to use product rule, and also both sides, numerator and denominator, require using chain rule. That will take you a while, but still doable. Try yourself if you want. I actually never done it. I think it's way too long. The idea is to use natural log for both sides, and then since log of product is sum of logs and log of quotients is different of logs, you'll just gonna have log plus log minus log, super simple here and there, and then differentiate each log, and then the answer follows right away. In this way, it's just more convenient. And the second case, and we're going to do this example right now, don't worry. The second case when we recommend you to use the log is when you have a function raised to a function. This is an interesting case, and maybe you saw in your homework something like 3x raised to the 3x, or whatever, for example. Why this is the issue? Note, 3 different cases. If I ask you to differentiate 3x to the 3, right? Then derivative is 3 goes down, it becomes 9x squared. That's what we call power rule. We already reviewed this power rule at the beginning of this video. What if you have 3 raised to x? That's exponential function, right? So that's going to be, I can do even 3x. 3 raised to the 3x. That's going to be 3 raised to the 3x times 3. That's exponential and chain rule. Exponential rule. Copy times derivative of the exponent. But if you have 3x raised to the 3x, that's basically input, which is some kind of function raised to the input, which is a function as well. That's what I mean by the notation of function raised to the function. Function raised to the function. This is neither exponential power, not a polynomial. The first case was polynomial, right? Polynomial. It's kind of both or neither. That's why we cannot use power rule and we cannot use exponential rule here, because this is not the function we knew before. And there's no special rule to actually do it fast. And this is exactly when you use logarithmic differentiation. Logarithmic differentiation will help you to get rid of this piece, because if you use log, this piece will go down, and then you will have a product instead. So let's do it. Both examples. We're gonna do both examples. We're gonna do the first one and the second one, since it's the last topic. Okay, let's do. The first one was this huge fraction. Let me copy it and use log for both sides to simplify it. Remember I told you that log slows down the processes. If you actually like coding, you know that products, quotients, and especially exponential functions, they take a lot of space in the computer. And that matters, because if you're ever going to be modeling something like cancer cell spread or even a move of one cell in the heart, I know that it sometimes takes 48 hours for a computer to calculate the move of only one simple cell with the thingies inside, and then how the cell interacts with other cells, and so on. 48 or more hours to just calculate one move of one cell, because that's how complicated it is. It might have 55 equations with 55 variables, which means 55 dimensions, and so on. That's why log is used pretty often in the situations when you need to release some space from the computer and speed up the process. If instead of the products, quotients, and exponential functions, computer just needs to add, subtract stuff, it will calculate things faster. So that in many cases, logarithmic function is used to speed up the processes. Well, it slows down the function, but then it makes the calculations fast for a computer. Too much talking, let's just apply natural log for both sides. Then I will have natural log of y equals, and then I will start working with the natural log on the right hand side. Natural log of the product is sum of logs. So I have log of 3x squared plus log of 7x to the 5 minus 3 raised to the 5. Log of the quotient is difference of logs, and whatever is staying at the bottom will have a negative sign. So x to the 5 minus 7 squared will be natural log of x to the 5 minus 7 squared. You see? You can do it step by step if you want, but actually it's pretty straightforward. Products, let me do red color. Products gives you sums, and in blue color, quotient gives you negative sign. Whatever was in the denominator now will be with a negative sign. And just not to make it confusing, this log is over here, like this, not in the denominator. It's basically log of the whole fraction. If you're already comfortable with this, you can start differentiating, but it will be upsetting not to use the power of the log to get rid of these exponents which are outside of the parentheses, not inside. That's very important. Not inside. You cannot use this law of logs for the exponents inside with sums and differences. Only input raised to the exponent will work. So I will take this 5 and put it down or multiply by it. Same here, this 2 can go down and multiply. Cannot do the same thing for this guy. Cannot do it because it's not outside. You see, it's not outside, it's inside. I will have natural log of y equals natural log of 3x squared plus 5 natural log of 7x to the 5 minus 3 And it's not raised to the 4. You're just putting this 5 down. Minus 2 natural log of x to the 5 minus 7. Some of you may be telling me that actually the first log can be break into log 3 and log x squared, and then 2 can go down. But that's, I think, too much work, because the derivative of log of 3x squared is not that complicated. Remember, we're using log to simplify the differentiation. If you think that the differentiation is relatively simple, you don't have to keep working with logs. Log is just a tool. Let's start differentiating. When we start differentiating, we're actually using implicit differentiation right now. Implicit differentiation starts right now, because y is not given explicitly. The left-hand side is always the same. 1 over y, that's because of natural log, times y prime. That's why usually, to save the space, we like writing it as y prime over y. And the left-hand side is always going to be like that. Now we just differentiate the right-hand side, which simplified. Derivative of log of 3x squared will be 1 over 3x squared times derivative of the function inside by chain rule, which is 6x. You see how I'm saving the space? Putting the times part right in the numerator. Now, 5 over 7x to the 5 minus 3 times, based on the chain rule, derivative of the function inside, which is 35x to the 4. And the last piece, basically we're almost done, minus 2 over x to the 5 minus 7 times the derivative of the function inside, which is 5x to the 4. This is almost the end. To find y prime, you have only one step left. Multiply everything by y. Logarithmic differentiation has one little difference between implicit differentiation. If you remember, with implicit differentiation, the answer includes both y and x, because we don't know y. That makes sense. It was never given. But when you do logarithmic differentiation, y is actually given. Here it is. Y is given explicitly. Here it is over here, if you want to use it in this notation. Y is given explicitly. That's why I'm gonna copy it again. And then the answer will be whatever I just calculated times the original function y. Don't forget. So it will be on, I will put it on the right over here. It will be standing over here waiting for you to simplify whatever you found. So everything in the green color times y. But y is given, so I can just do over here. So that's my y. Well, if you want, you can simplify whatever we did over there, because 6 over 3 can be simplified, and x squared can be simplified. It's going to be 2 over x, not too bad, plus 5 times 35, x to the 4, becomes 5 times 35 is 175, x to the 4 all over 7x to the 5 minus 3. Do not simplify x to the 4 and x to the 5. You cannot simplify or cancel out things if there is a negative or positive sign in the numerator or denominator. We could simplify in the first place because it's just products and quotients, that's it. Minus 2 times 5 is 10, x to the 4 all over x to the 5 minus 7. And then everything is multiplied by y. And your y is given, so you don't keep it just y. As you can see, with logarithmic differentiation, the answer should not include y. Should not have y, because BC, y is given at the beginning. So just go back at the beginning of the question and put it there. Was it hard? What do you think? Can you do it by yourself? Can you do it fast enough, though, for the testing purposes? One more, and it's going to be the last problem for today. 3x raised to the 3x. 2. how to differentiate y equals 3x raised to the 3x. That one is actually pretty fast. Since we don't know how to differentiate this function, it's not power rule or exponential rule, we're going to apply log for the both sides. Natural log of y is natural log of 3x raised to the 3x. Log allows me to put this 3x down, and now it's not anymore a complicated function. Now it's just a product of 3x times a logarithmic function of 3x. Look at that. That's a product rule. U times v. So basically from whatever we didn't know, that guy we didn't know, we created something we do know. That's the idea. Now start implicit differentiation. Again, it will be y prime over y on the left hand side and product rule on the right hand side. So I'm going to have derivative of 3x, that's 3, copy natural log of 3x, plus copy 3x, differentiate natural log of 3x. You could write it down as log 3 plus log x, but it's a little bit too much writing, I think, because derivative of log of 3x is not very hard. It's going to be 1 over 3x times derivative of 3x, which is 3, and it cancels out. Do you remember the last step? Y prime equals 3 natural log of 3x plus, actually I will not even cancel this out. I will cancel instead the whole 3x part and 3x part. That's even cooler. So it's going to be plus 3. Is that all? Nope. Don't forget to multiply. Let's use another color. Don't forget to multiply by y. And y is actually given as 3x raised to the 3x. So I'm going to put brackets. And then it's going to be 3x raised to the 3x. And that's the answer. If you have to take the exam and you see multiple choice part, always look for the answer that involves the original function if you need to do logarithmic differentiation. As you can see, 3x to the 3x is my original function. And then the part inside will be the result of the product rule. We had 3x times natural log of 3x. Seems to me we did not do any mistakes, so that's gonna be all. We reviewed product rule, quotient rule. We reviewed chain rule many times, even chain rule twice or 3 times in a row. Then we reviewed implicit differentiation, logarithmic differentiation, and derivative of cosine, sine, tangent, secant. We also reviewed the derivatives of arc cosine, arc sine, arc tangent. And that's all we need you to know for now. And that's actually a very important part of calculus, sequence, and mathematics. This will be a core information for physics, engineering, chemistry, biology, and even medicine. Now go and practice more. The more you practice, the better it gets. So that's the best recommendation I can give you. Practice like crazy. Practice like you're crazy in love with that. Because if you want to know why I'm so good at it, or your friends are good at it, or someone you know is so good at it, we just practiced like crazy. There's no way around it. People who practice it, they're good at it. People who did not practice it, they are either bad at it or okay with it. Everyone had to do it, so I guess you have to do it as well. Good job for watching for such a long video, and see you next time.